Okay, so in the last video we have seen what the diameter and the radius of a graph are. So we are going to start off today with this inequalities. Radius of a graph G is less than or equal to its diameter, which is less than or equal to 2 times the radius of G. Now before we prove these inequalities, we have to interpret them properly because these are not always real numbers. The definitions of radius and diameter allow for these quantities to be infinite also. So what will these inequalities mean in case one or both the quantities are infinite? To make sense of that, we consider the extended real number system, which is the set of real numbers along with the two symbols minus infinity and plus infinity, which are not real numbers. Now on this set we have an ordered relation, just like we have an ordered relation on the set of real numbers, which allows us to say which real numbers are less than which ones. And in this context, the elements in R star are called extended real numbers. So an extended real number is either an ordinary real number or minus infinity or plus infinity. And the order relation we have on R star is defined like this. For two extended real numbers, we say A is less than or equal to B. We are using the same symbol for the ordered, for this ordered relation also. If there are three conditions, condition 1, A is minus infinity. Irrespective of what B is, in that case we will say that A is less than or equal to B. Number 2, B is plus infinity. In that case also we have this relation. Number 3, A and B are both ordinary real numbers, and as ordinary real numbers A is less than or equal to B, where this is the ordinary order relation we have on R. Okay, so with this definition we have a new order relation which is a natural extension of the order relation on R. Now in this new system, in this system of extended real numbers, we have to interpret these inequalities. So that is one thing. So for example, if of course these quantities, none of them ever becomes minus infinity, that is coming from the definition, but this plus infinity is a possibility. So that is taken care of by this definition. And plus infinity usually is just simply written as infinity because we have used this symbol in the definition. Okay. One more thing is this: if say radius of G is infinity, then what is the interpretation of 2 times infinity here, where we seem to be multiplying 2 and infinity? For that we additionally define this: if we multiply a positive real number with infinity, then the result is defined to be infinity. For every real number A with a greater than 0. Okay, so with this, in this extended system, with all these things taken care of, now the inequalities have a meaning. Now, because these can be infinite or finite, so naturally two cases arise, and we are going to consider the two cases depending on whether diameter of G is finite, is a real number, or is not a real number, that is whether it is infinity. So let us consider the infinite case first. Assume diameter of G is equal to infinity. Then by the definition of diameter we have this. Then there exist vertices U and V in G such that the distance between U and V is infinity, and this happens when there is no path joining U and V in G. That is, G has no path joining U and V. Okay, we are now going to show that under this condition radius of G will also be infinity. So let us take an arbitrary vertex. Let W belonging to V of G be any vertex. If G has a path joining U and W and a path joining W and V, then G has a path joining U and V because if say you have the vertices U and V here somewhere in the graph, and you also have the vertex W. Say there is a path in G joining U and W and one joining V and W, then they can be combined to give us a path joining U and V in G, which would contradict this thing that G has no path joining U and V. So that means what? It means that either there is no path joining U and W in G, or there is no path joining W and V in G, or both. That is, there is neither in a path joining U and W nor a path joining W and V in G. So either G has no path joining U and W, or G has no path joining W and V, or both, of course. That we need not write, because whenever we use or in mathematics, it usually means inclusive or. Something or something else means either that thing is true or the other thing is true or both are true. That is, either the distance between u and w is infinity, or the distance between w and v is infinity. And in the context of these arguments, we should perhaps mention that we have dropped this subscript g simply because here we are dealing with only one graph. So whatever is happening in that graph. So there is no need to clutter the notation by writing additional symbols. Okay, so we have this. Now the point here is that, you see, what we have shown here, w was any vertex in the graph. Then for any such vertex, there is at least one point which is at an infinite distance from that vertex. This means that the maximum of the distances of w from the vertices of G, say w prime, where w prime is any vertex in G, is infinity, because one of these quantities, as w prime varies over the vertex set of G, is infinite. So the maximum is also infinite. And note that these maximum, minimum, all these things have to be interpreted in the extended real number system. Okay. Which implies that the radius of G, which is the minimum of all such maxima, as we vary w also, that is distance between w and w prime is also infinity. So here the minimum that we are taking is of a set, all of whose elements are infinity. Okay, so naturally the minimum is also infinity. So if diameter is infinity, radius is also infinity, and in this case these inequalities become equality, keeping in mind this thing, because now in place of a we can take 2, and in place of infinity we have radius of G. So in this case, radius of G is equal to diameter of G is equal to 2 times radius of G is equal to infinity. So this is the case when diameter of G is infinite. Now we are going to consider the case that diameter of G is a real number. Next, assume that this is a real number. In other words, it is not infinity. Then there exists vertices, since we are considering a new case, it won't hurt to use the same symbols u, v, w, because those are anyway just names given to variable names. U and v belonging to v of g such that the distance between u and v is equal to the diameter of g, because the diameter by definition is the maximum possible distance between vertices in G. So at least two vertices should be there that will give us this distance, which is the maximum possible. There may be multiple such pairs of vertices, but at least two vertices will be there. At least one pair is there, which will realize this diameter. Okay. Now let W belonging to V of G be a central vertex. As a graph G has a center, whatever it is, that center has vertices in it. We have chosen one such vertex, W, it's a central vertex. Since so by the definition of radius, this is the maximum distance of W from the vertices in G we have distance between U and W less than or equal to radius of G. Okay, because since W is a central vertex, radius of G is the maximum distance of W from the vertices in G. We have already seen these things in the previous video. You have W, you calculate the distances of W from all the vertices in G. The maximum distance is the radius. So in place of that, if you take say this vertex, which is some vertex in G, U, then this distance will be less than or equal to radius. Then you have W here and you have U here. This U may or may not give us the radius value, but it is always less than or equal to the radius. Okay. And similarly, the distance between W and V, you can also write V and W, it does not matter, it's the same, because this D is after all a metric on the set of vertices, making the graph a metric space, if you know what these things mean. And this is also less than or equal to the radius of G. Hence, diameter of G, which is the distance between U and V, is less than or equal to the distance between U and W plus the distance between W and V using triangle inequality. So that is less than or equal to 2 times radius of G. So we have got the second inequality. Also, since let's write this in the next line, is the maximum possible distance between the vertices of G and radius of G is after all a distance between two vertices in G. We have radius of G less than or equal to diameter of G. I see one thing now that I should have done, I should have said this one first. You see, now our case is the case where diameter of G is finite. Okay, but before saying that, let us just make sense of this, what I have written here. Radius of G by definition is this, minimum of, say, minimum as B varies over V of G, of maximum as A varies over V of G, of the distances between A and B as A and B vary. Now if A is a, no, not A, if B is a central vertex, then the distance, okay, instead of arguing like this, let me put this argument forward. Say you have a central vertex W in the graph, then the radius, just like here, is the maximum distance between W and the vertices of G. Whatever this distance is, it will come because of some vertex, say W prime, so that this radius of G is equal to the distance between W and W prime, and diameter of G is the maximum possible distance among all distances. So naturally this is less than or equal to diameter of G. Now why I was saying that I should have said this part before concluding these things is because this one tells us in particular that radius of G in this case is finite, it's a real number, and that's why when we are adding radius of G with radius of G, we are getting 2 times radius of G. But in this case we are not we don't have to deal with infinite quantities. So ideally, if you want, you can write this part instead of writing also, you argue this part before arguing this second inequality, arguing for the second inequality, and this way you have both the inequalities true in both the cases, as the diameter of G is infinite and also when it is finite. So the inequalities have been proved entirely. Okay. Now the author says something about these parameters, diameter and radius. Diameter and radius are not related to minimum, average or maximum degree. They are not related to these other parameters if we don't say anything about the order of the graph, that is how many vertices the graph has. If we don't restrict that in any way, then these parameters don't have any relation. Any one of them, say diameter and minimum degree, they can be given any value. Such graphs can be found if you can increase the diameter, you can decrease the minimum degree, which I think you can see why that is true. For example, you can keep the minimum degree as small as possible, but you can keep on increasing the diameter. Just consider a path with as many vertices as you want. In a path, the minimum degree is 1, which belongs to this vertex as well as that other end vertex. But the longer you take the path, the more diameter the corresponding graph, I mean the path is also a graph, the more the diameter will be. At the same time, if you can make the diameter have any value, but you can keep on increasing the minimum degree. You just take, I think this type of graphs are called star. They have a name. We will come across these things when we go further into the theory. This graph has diameter 2 because the maximum possible distance between any two vertices is 2. But the minimum degree, we cannot say minimum degree. This way we cannot increase the minimum degree because we are still having vertices of degree 1. Okay, so you take the complete, yes, that is actually the example that I was trying to present. Kn, the complete graph on n vertices. Because that graph is complete, the distance between any two vertices is 1, so diameter is 1. But minimum degree keeps on increasing because you see, in a complete graph with n vertices, each vertex has degree n minus 1. It has all the vertices as its neighbor except of course itself. So that way these parameters are not related. But if we say something about the order of the graph, if we restrict the order in some way, then they become related. We are going to see that thing. If we don't say anything about order, order means order of the graph in question. However, graphs of large diameter and minimum degree are clearly large. if a graph has large diameter, then it should have two vertices which are far apart, okay, where the distance between them is quite large. So to get that distance, you should have a path of that length joining them. That path should have many vertices in it as parts of it. So the number of vertices increases just simply because the diameter is large. Even when your graph is just a path, if there is no other vertex, then also as the diameter increases, the number of vertices automatically increases, so the order increases. So if a graph has large diameter, then the graph itself is large in terms of its order. Similarly, if a graph has large minimum degree, then also it is large, because you see that minimum degree will of course be the degree of some vertex. So that vertex will have many neighbors. So automatically many vertices are coming as parts of the graph. And since that is the minimum degree, the other vertices will have even more neighbors, or the other vertices may have the same number of neighbors or even more neighbors, so making the order even larger. So that's why the author says graphs of large diameter and minimum degree are clearly large. So individually, if diameter is large, then the graph is large. If minimum degree is large, then also the graph is large. But if both these two things are large, if both the graph is it has high diameter, at the same time it has high minimum degree, then the graph becomes much larger than what these parameters force alone. Okay, so there is a remark here in brackets, much larger than forced by each of the parameters alone. And for this we have to see exercise 8. We haven't seen the exercises. We will get to the exercises once we finish the these elementary things. We will then see all the exercises at the end of chapter 1. We are still in chapter 1. On the other hand, graphs with small diameter and small maximum degree are small. And small maximum degree, we are just simply writing small ones. And which precisely the statement is this. This is a proposition. We are going to now state it and prove it. Proposition 113. A graph G of radius at most k and maximum degree at most d, where d is greater than or equal to 3, has fewer than this many vertices, d divided by d minus 2 times d minus 1 to the power k vertices. Okay, we are saying that graphs with small diameter and small maximum degree should be small, but here we, in the statement we see radius not diameter, but small radius automatically means small diameter. Because of that inequality we have proved that diameter is less than or equal to 2 times radius. I am not writing the graph, just simply to show you what inequality we are using here. So if radius is small, diameter is automatically small. Now if our graph has radius at most k and maximum degree at most d, then we have to show that the graph has fewer than this many vertices. Of course, you should not think that this many vertices means that there is a graph having exactly this many vertices, because this may not be an integer since we are dividing by d minus 2. All the proposition is saying is that our graph should have an order that is less than or equal to this real number. That's what it is saying. Okay, we are now going to prove this. We start the proof by considering a central vertex. Let z belonging to phi of g be a central vertex, that is a vertex in the center of G, and for any non-negative integer I, let us write here, let di be defined to be the set of those vertices in G whose distances from this central vertex Z are exactly equal to I. Okay, say di is this set. Clearly, the number of vertices in D naught is 1. There is only one vertex that is at distance 0 from Z, namely Z itself. So that's why this is 1. And what can we say about D1? D1 consists of those vertices which are at distance 1 from Z. That means which are neighbors of Z. Precisely this is equal to the degree of Z. And because the degree is less than or equal to the maximum degree, so this value will be less than or equal to D. this is less than or equal to D. In general, for any integer I less than k, for any non-negative integer I less than k, we have the number of elements in di plus 1 is less than or equal to d minus 1 times the number of elements in di. Why? The reason given by the author is this. This is because every vertex in di plus 1 is a neighbor of some vertex in di, that is one thing, and each vertex in di has at most d minus 1 neighbors in di plus 1. Additionally, since it has another neighbor in di minus o, we are mentioning I minus 1. So that means we have to allow, we cannot take I equal to 0. We cannot take I equal to 0. Fine, if we are not taking I equal to 0, that case is taken care of by these two special things. Because okay, we will see that trivial case later. Let us first try to understand what the author is saying here and how that implies that this inequality is true. I think this space won't be enough for the explanation. We have to draw a figure. We have the central vertex Z here, somewhere in the graph. Okay. Now, the first part of these justifications is that every vertex in di plus 1 is a neighbor of some vertex in di. Let us see. So this is di plus 1, which is a set of some vertices. So we consider an arbitrary vertex, say v in di plus 1. The fact that v is in di plus 1 means that v is at a distance I plus 1 from z. So there is a path joining z and v that is of length I plus 1. Now look at the neighbor of v in this path, that is this vertex. I think it will be better if we just draw it like this, it will be more prominent. Consider this vertex. This vertex is at distance I from Z. Let us also call this vertex, say, V prime. Why is the distance between Z and V prime I? Because this path joining Z and V is a path of least possible length in G. Now, if you say that there is a smaller path in G joining Z and V whose length is smaller than I, then that path along with this edge will give us a path joining Z and V whose length is smaller than I plus 1, contradicting the fact that the distance between Z and V is I plus 1. So that is why this path which joins Z and V prime is a least path joining Z and V prime, and as such the length of this path must be the distance between Z and V prime in our graph, which is I. So because this distance is I, so V prime belongs to Di, and that is why the author is saying that every vertex in Di plus 1 is a neighbor of some vertex in Di. Fine, we have understood that. And each vertex in Di has at most D minus 1 neighbors in Di plus 1. Okay, to understand that, you think like this. You have a vertex W prime in Di. It has some neighbors and it also is at a distance I from Z. The distance between Z and W prime is equal to I. Now it has some vertices here and there. It has some neighbors. Now these vertices that are neighbors of W prime, each one of them has some distance from Z. That distance is either I minus 1 or I plus 1. Why? You see, if the path join, say we consider this vertex. If the, see, so what was my argument? My argument is this. Already there is a, for specificity, let us also call this vertex W double prime. I hope things are not confusing. This is V prime. Okay, that we have left that part. Now we are here. This W double prime is a neighbor of W prime. Now already we have a path in the graph that joins Z and W double prime, which is this path along with this edge, and it is of length I plus 1. Okay, so that means the smallest possible length between, or the smallest possible distance, or in fact I should say the distance between Z and W double prime should be less than or equal to I plus 1. Now if it happens that this distance is, okay, it can be I also, no? I said it should be either I plus 1 or I minus 1. That is not necessarily true. It can be I also. It can either be I plus 1, or that is coming from this inequality, it can be I, or it can be less than I. If the distance is I plus 1, then clearly that vertex belongs to di plus 1. If the distance is I, then this vertex belongs to di. If the distance is less than I, then the vertex will belong to some lower di, I mean some di minus 1 or I minus 2, something like that. Okay. Now the point we are making here is this. That the distance cannot be less than I minus 1, because if the distance is less than I minus 1, then clearly there is some path joining Z and W double prime whose distance is less than I minus 1. If you then take that path and this extra edge joining W double prime and W prime, then you get a path of length less than I, that is less than I minus 1 plus 1, proving that the distance between Z and W prime is less than I, which is false because it has to be exactly equal to I. So this possibility is not there. So if this inequality is true, then the distance between Z and W double prime is equal to I minus 1. So that means the neighbors of W prime are of three types. Some of them are here in di minus 1. Some of them are here in di, and some of them are in di plus 1. So the statement here is this: each vertex in di has at most d minus 1 neighbors in di plus 1. Clearly, if the vertex W prime in di has neighbors in di minus 1, then the vertices in di plus 1 which are neighbors of W prime, they decrease in number. The more vertices we have here at the lower level, the less vertices we have here at the next level. However, in the extreme case where there is almost all the vertices of W prime, that I mean almost all the neighbors of W prime are in di plus 1, there is at least one vertex which will be in di minus 1, and that will come from the path that joins Z and W prime. It will be that vertex which is lying in this path and which is adjacent to W prime. It must belong to di minus 1, because that is a path joining Z and W prime that is of minimum possible length. So that's why I myself keep forgetting this thing. What we are saying here is that each vertex in di has at most this many neighbors in di plus 1. The number of neighbors of this W double prime, or W prime actually, is clearly degree of W prime. Now that degree is clearly less than or equal to the maximum degree. So in the extreme case where all the neighbors of W prime are in Di plus 1 except one neighbor, the number of vertices in Di plus 1 that are neighbors of W prime is at most D minus 1. It is actually at most this. The number of vertices that are neighbors of W prime in Di plus 1 is less than or equal to this, which itself is less than or equal to this. So we have understood why these things are true. Now, how are these things implying this inequality? That is the next question. To understand that, we are going to, so this part we have understood. We are going to look at Di and Di plus 1 again. Every vertex in Di plus 1 is a neighbor of some vertex in Di, and each vertex in Di has at most D minus 1 neighbors in Di plus 1, and we are forgetting this, we are not considering this neighbor of that vertex, which of course is in Di minus 1. So note that, what does this tell us? It tells us that if we classify the vertices in Di plus 1 according to the vertices in Di of which they are neighbors, then for each vertex in Di we are getting at most Di minus 1 neighbors, or at most D minus 1 neighbors, or for each vertex in Di we are getting at most D minus 1 neighbors in Di plus 1. So each vertex here is giving us at most D minus 1 vertices there, and every vertex in Di plus 1 is appearing like this, because every vertex in Di plus 1 is a neighbor of some vertex in Di. Now we are not saying that these sets of neighbors are all disjoint. You may have a vertex that is adjacent to, you may have a vertex in Di plus 1 that is adjacent to more than one vertex in Di. That may happen. But the thing is that the number of vertices in Di plus 1, if you look at them in this way as clumps, okay, as subsets, then that is less than or equal to what? D minus 1 plus D minus 1 plus D minus 1, a number of D minus 1s, where each D minus 1 is coming from that vertex, okay, whose neighbors are here like this. Why we write less than or equal to? That is because there may be overlappings, there may be intersections. Only when these vertices have distinct neighbors in Di plus 1 we have equality. Otherwise the number is smaller than this sum, smaller or equal to in general. And how many D minus 1s? because the d minus 1 part is coming from di, so this is times d minus 1. That's why we are that's how we are getting this inequality. So you get the point, I hope. The vertices in di plus 1 have been considered in clumps as neighbors of vertices in di. These clumps may overlap. Okay, there may be common intersections. So as clumps, they are giving us at most this number, and each vertex in di plus 1 is appearing in some clump that is coming from one vertex in di. So that's why this takes into account all the vertices in di plus 1, and this is the maximum possible number of vertices. So that is how we are getting these inequalities. Now we can proceed with the rest of the proof. Note that the vertex set of G is the union of these di's as I varies from 0 to k. Oh, we didn't say anything about k. No? K is the maximum possible value of the radius. So because we are considering our distances from the vertex Z, from the central vertex, the maximum possible distance is equal to the radius, whose value itself is less than or equal to k. So when we are considering this union of all the di's, we have to consider till dk, because the distance of any vertex from Z is less than or equal to radius, so it will be less than or equal to k. So the maximum possible value that any distance of a vertex from Z can be, that is k. It will not go higher. So we have all the vertices within this range. So that's why we are having V of G is equal to union of these di's. Now if we use these inequalities one after another as we change the value of I, we get this. This is less than or equal to d minus 1 times the number of elements in di, which itself is less than or equal to di minus 1, that is equal to d minus 1 square times this. Like this we can continue, and we will ultimately get to this. D minus 1 to the power I times number of elements in D1. You can see why that will happen. When we have 2 here, we are subtracting 1. We are subtracting 1 less from D. when we have subtracting 1 less from I. When we have I here, we will have to subtract analogously 1 less than that from I. So that gives us this 1. So we get to this, and this number, this cardinality itself is less than or equal to d minus 1. We have already seen this. So this is less than or equal to d minus 1 to the power I plus 1, and these things are true for all I less than k. What happens when we take I equal to 0? What happens to this inequality? When we take I equal to 0, then here the set is D1. Number of elements in D1 is less than or equal to d minus 1 to the power 1. So we see that, let us just write that. Note also that or in fact we should write the other way around. This we already know, and d minus 1 is this. So okay, so we have got these upper bounds for the sizes of the sets di. So the order of G is equal to, note that this union is actually a disjoint union, because a vertex that is at distance I from that central vertex Z cannot be at any other distance from Z simultaneously. So each vertex in G belongs to exactly one di, and that is why this is equal to the number of elements in D0, in D1, like that. But we don't really know whether we will be able to go till k. We will be able to go till the radius of G. The maximum value of the subscript will be the radius of G, because that is the maximum possible distance at which any vertex can be from the central vertex Z. Let us just write everything in full detail, and then we will write inequalities. D radius of G. Do you see what we have done here? This is the maximum possible distance that any vertex can be at from Z, and that is less than or equal to because k itself is greater than or equal to the radius is at most k. Okay, now we use the inequalities we have here. This we already know, this is 1, this is equal to 1, but for the other terms we have inequality, so we are writing inequality. 1 plus d minus 1, another term will be, it will be nice to write another term. For d2 we will have, so the subscript and the exponent are the same. And this now becomes a geometric series, a finite geometric series. So its sum will be equal to d minus 1 to the power k plus, am I writing it correctly, divided by minus 1 divided by d minus 1 minus 1. So that is, we have got d minus 2 in the denominator. Now if I don't write minus 1, then we are clearly writing more. Just like that, among the factors d minus 1, d minus 1, if we decide to write d in place of one of them, then again we are writing more. So this is less than d divided by d minus 2 times d minus 1 to the power k. So that gives us this upper bound for the order of G. So G will have at most this many vertices. So that completes the proof. The part which involves this inequality, it's somewhat difficult to understand that part, or at least it's difficult to understand from these remarks what the author is trying to say. But I think we have understood properly how these things are a justification for these inequalities. So this way, if our radius of the graph is bounded and also the maximum degree is bounded, then the order is bounded in this way. Similarly, one can bound the order of G bounded from above. Okay, this is an upper bound for the order of G. We can find a lower bound also from below by assuming that both its minimum degree and girth are large. There we said that maximum degree and radius are small. If that is the case, then the graph is small. Here, if minimum degree and girth are large, then the graph is large. That is, we can give some lower bound for the order of the graph. For any real number d and any natural number g be defined a number denoted by n naught of d comma g, and the number is defined like this. It is equal to 1 plus d times summation of d minus 1 to the power I, where I is varying from 0 to r minus 1, if g, which is 2r plus 1, is odd, or g is given from g. If g is odd, then this r is coming from g, it is defined by g. So we have the colon here. So r has its definition in terms of g. R is actually g minus 1 divided by 2, and g is given. If g turns out to be odd, then because of for that r we have this, and it is defined to be 2 times summation of again d minus 1 to the power I, where I is varying from 0 to r minus 1, if this is even. Say we define our quantity like this. It is some number defined in terms of the real number d and the natural number g. It is not difficult to prove. Now we are going to make a statement with the help of this n naught d comma g. It is not difficult to prove that a graph of minimum degree delta and girth g has at least this many vertices, n naught of delta comma g, and we will do this in exercise 6. One can obtain a similar bound for its average degree, for the average degree of the graph. And there is a theorem whose proof is not given. It was proved in 2002. And these are the authors. And lineal. The statement is this: let G be a graph if the average degree of G is at least D, which itself is at least 2, and the girth of the graph G is at least small g, which is a natural number, then the order of G, that is the number of vertices of G, is at least n naught of D comma G. We get the same lower bound for average degree and girth. Okay. Now, one aspect of theorem 134, this theorem, is that it guarantees the existence of a short cycle compared with the order of G. It guarantees the existence of a short cycle as compared with the order of G. Using just the minimum degree version of exercise 6, I need to refill. Give me a moment. Using just the easy minimum degree version of exercise 6 that we were mentioning here, we get the following. There is a corollary. These estimates of these bounds may not seem like much, but they will help us eventually in our study of graphs. They will be extremely useful while saying something about the order of the graph. We cannot always expect to find everything exactly its exact value. Sometimes bounds also become very useful. We will see why in due time. So the corollary is this: if G is a graph, then there is a hypothesis such that its minimum degree is at least 3, then the girth of G is less than 2 times log the order of G. Recall that for us in this book, logarithm, if we just see log, it means the base is 2. If we mean natural logarithm, for that we will write ln. Proof is not very difficult. You just have to use that result. If the girth, which let us denote it by G, is even, if the girth is even, then what do we get from this bound, this lower bound? N naught of 3 comma G is equal to, you just use that formula, the definition of the numbers N naught. If it is even, then this is 2 times, if you sum that series that you have in the definition of N naught, it turns out to be equal to 2 to the power G by 2 minus 1 divided by 2 minus 1, which is equal to 2 to the power G by 2, 2 times 2 to the power G by 2 minus 1, which is greater than 2 to the power G by 2. Why is that so? You see, this just the last inequality tells us that 2 to the power G by 2 is greater than 1. The minimum value of G, okay, do we have any bound for the minimum value of this girth? Because delta of G is greater than or equal to 3, girth, of course, it is greater than or equal to 3 because it's the length of a cycle after all. No, it cannot be smaller than 3. So since small g is greater than or equal to 3, small g by 2 is greater than 1. So 2 to the power G by 2 is greater than 2, 2 to the power 1, and that's why, which is greater than 1. So 2 times 2 to the power G by 2 is greater than 2 to the power G by 2 plus 1. In other words, we have this. So that's how we are getting this inequality. While if G is odd, then what happens to this? N naught of 3 comma G is equal to 1 plus 3 times 2 to the power G minus 1 by 2 minus 1 divided by 2 minus 1. We have not considered 1 in this sum, and the rest of the terms, I mean in the definition also we have that extra 1 plus d times that sum. Okay, so this is equal to, which is equal to, if you calculate, if you simplify the things, it will become 3 divided by root 2 times 2 to the power G by 2 minus 2, and this again by a similar argument as the previous one is greater than 2 to the power G by 2. So we see that whatever the parity of the Girth be, whether it is even or odd, this number is always greater than 2 to the power G by 2. Since order of G is greater than or equal to this lower bound, we thus have strict inequality here. So here also we will have strict inequality, or G by 2 less than this, or G less than 2 times So you see that this result is actually quite general. If you have any graph whatsoever whose minimum degree is at least 3, then the girth should not exceed this number. That's why we say that there is at least one cycle which is quite small compared with the order of the graph, because girth having this small value means there is a cycle with that length. That cycle is small compared with the order of G because we have logarithm. So for example, if G has say 2 to the power 16 vertices, which is quite large, then if our graph has minimum degree at least 3, then the girth is less than 2 times this, which is 2 times 16, that is 32. So G has a cycle, at least one cycle, whose length is less than 32, which is much smaller than the order 2 to the power 16. And lastly, there is this notion of walk. We have seen path, and now we have another such thing known as walk. A walk of length k in a graph is an alternating sequence V naught, E naught, V1, E1 like that up to V k minus 1 E k minus 1. Let us just write V k minus 1 also, Vk of vertices and edges starting and ending with vertices such that EI is the edge joining Vi and Vi plus 1. That is, the edge that appears in between two vertices is an edge joining the vertices, is the edge joining the vertices, Vi and Vi plus 1. For all I less than k. If V naught is equal to Vk, we say that the walk is closed. A closed walk and open walk, natural things, natural terminology. If the vertices in a walk are all distinct, then there is naturally a path. Then it defines an obvious path in the graph. Okay, by the way, how is a walk different from a path? Let us see from the definition. Let's take a concrete graph and see a specific walk in that graph. Say we have this graph. We can draw the edges any way we like and let this be its vertices 3, 4, 5, 6, and for ease of notation, let us denote the edges also by some, let us give the edges some names: E1, E2, E3, E4, E5, E6. Then we can consider this walk 1, E1, 2, again E1, 1, E2, 4, E4, 3. Note that the walk as we see it is actually not a path. It's the walk means it's a walk, as if someone is walking. A person is starting from here, then he goes to E2, the vertex 2, following the edge E1, and then again he comes back to E1 following that same edge. So this walk is like this, then this. Okay. Now if the vertices in a walk are actually distinct, here the vertices of course are not distinct, we have a repetition here. If the vertices are distinct, then obviously there is a path joining the beginning and end of the walk. Now if we continue this walk like this, E4 3, E3 2, E1 1, then this would be a closed walk. Here, then from there, here, this and this, because it starts from 1 and comes back to 1. So this is a closed walk. In general, every path or every walk, not every path, every walk in a graph has a path between two vertices in a graph has a path joining these vertices. For example, this walk between 1 and 3, which looks like this, it has the path joining 1 and 3, which is this. Okay, in every such case, if you think of it, if you remove the repetitions of going to a vertex and then again coming back from where you started, if you remove those things, you will be left with a path. That means there is some path inside a walk joining two vertices which are the beginning and end of that walk. So here this section ends. After this, in the next video, we will start a new section where we will explore the notion of connectivity. We already talked about it a little in the previous video, how one can get a disconnected graph if one removes some special types of vertices and edges from the graph known as cut vertices, cut edges. So we will see those things, and the number of components a graph has and how that is related to the other parameters of a graph. So that will be explored in the next part. So with this, we end the video here. If you have any doubts regarding these things, or if you want to discuss about these things, you can either comment in the comment section below, or you can mail me here. So that will be all for today in graph theory. So until the next video, it's me, Lucifer, from a mathematical room. Have a nice day.